west and a little further south than your Ottawa. And as a funny anecdote, funny story, at least I'm able to laugh about it now. A couple years back, I was flying into Ottawa, and I was detained because they thought that was a completely made-up place. And I claimed, well, just Google it, and that's not the right thing to say to an official. But an hour and a half later, so I was on my merry way, having shared Ottawa, Kansas, which, interestingly enough, did speak French until the 1870s, where then they adopted into English and became part of the United States. Interesting little bit of history there. So, as some additional background, our company, Water Systems Engineering, is a troubleshooting lab. And so we've got a lab and we've got a mix of engineers and geologists. And people come to us with problems in wells, in pipelines, in storage tanks, filter systems, and so forth. So that's where the water systems comes part. So the information I'm going to be sharing with you is from that context. So kind of like, calling 911 to say, hey, have a great day. People only reach out to us with samples when, we're talking about post-mortem on a well, or there's a water quality impingement or something like that. So in a sense, the information I'm going to be sharing with you is a little skewed, but that's where we have our biggest challenges as an industry, when we've already gotten to that point of a train wreck, or we're nearing that train wreck. So I'm going to talk about well fouling, and I'm going to beat this term up throughout the day, so I thought I would give just a little background on what I see as that. And I do this because it changes. It's going to mean something different in British Columbia, it's going to be something different in Kansas, New Jersey, and so forth. So just so we're all kind of on the same page, it's a water quality impairment. It's scale accumulation, biomass or slime buildup. It's fine sediment that is infiltrated in. Corrosion, maybe coming from a stray current or a galvanic cell that's formed within the well, or even microbial influenced corrosion. It's a pathogen occurrence, so it's causing a water quality issue. Or an aesthetic issue, which sometimes can cause faster problems with the customer than a water quality issue, like taste, odor, or discoloration. So it's anything that impacts the use and the usability of the well and the produced water. And so with that basis, I'm going to jump in. It can be biofouling. We've got a severe mix of biologically related fouling and entrained precipitates right above the screen zone, and you can see it's starting to infiltrate into the screen zone there. This presented itself as periodic slough-offs. That would decrease the efficiency of the pump and certainly the quality of the produced water. This, unfortunately, was a relatively new well, only about 18 months old, that sat out of service while they waited for pump and infrastructure to be built out to it. Got the pump set, turned on the well, and just nasty. Rotten egg odor, discoloration, very putrid smelling. And what had happened is the well had not been fully developed and had turned anaerobic, and sulfate-reducing bacteria had grown up in that time period of sitting stagnant. Got a hole in the casing, bad enough. Causes an aeration of the water, but also we were getting formation influence. And so the operator couldn't maintain a chlorine residual, so we pumped the well a little bit harder to kind of flush things out and started to get formation material in, started to do just a little bit of damage to the pump. Fortunately, we decided to run a video before they went any further and discovered this. One of the most common problems we see is iron bacteria related, and it presents itself with slight increases in your total iron readings. If you've got an iron removal filter, you'll start to see it to be less efficient. Periodically, depending on how the well is operated, you'll see a surge of iron-rich water. It might be slight orange like this, some might be slightly discolored. In larger well systems, it's generally when we have a pump problem and we pull it and we can see fine buildup throughout the pump and motor assembly. My daughter likes to call this one cold brew. This was a large well in Utah, and it was mandated that because of water conservation efforts, they said to this well, they idle it for 6 months a year. And as it does, the anaerobic kind of takes over. You see a lot of manganese mobilized from the formation. When you turn it on, you've got this thick, highly unpleasant water being produced. The challenge here is how do you clean this and then also educate the customer. You know, your conservation efforts are great, we appreciate that, but we're actually wasting more water to clean this up so we can run it the other 6 months of the year. So sometimes the solutions are not always a hammer. Sometimes we've got to really sit down and get what I call the whole shareholder discussion going on. So I'm going to be talking about testing. And as an industry, when do we test? Well, we test for new well construction. Part of that is to see if the water is going to be suitable for our uses. And that's going to be different if it's a backyard residential well, a larger municipal well, let's say a well that's supplying a pharmaceutical or a food processing plant. And also from that, we can get information on the design and construction. So can we utilize mud rotary? Can we utilize low carbon steel or galvanized? Or do we need to look at high strength, low alloy, or PVC, or stainless steel? Then we can look and see regulatory requirements. And that might be because we just cleaned the well, or that we had a storm event and we need to prove that the well is disinfected in good order, or there may be something of regional concerns. For example, nitrates. I come from a big ag community, so we're constantly monitoring for nitrates. Other parts of the country and continent, we're looking at arsenic, or manganese, or selenium. And then failure or maintenance concerns. And unfortunately, this is, like I joked about earlier, usually post-mortem. We've already reached that point of impingement on operation or water quality. Hopefully, with some of the information you get today, if you start to see problems or you're monitoring a well, you can utilize some of the testing values as far as identifying the problem before it runs to failure. So I have a lot of customers, residential, municipal, industrial. Well, we test enough as it is. How come we didn't find this out? And it's a lot of times it's the same testing methods, but we're looking at it in a different light. Did it reach the maximum contaminant level of the MAC, or is it just starting to build up? And so it's the same type of testing, and not to knock regulatory concerns. I mean, with our regulatory guidelines from Health Canada or the Environmental Protection Agency in my country, we've delivered billions of gallons of water at a fraction of the true cost of it to a largely unappreciative client. You know, so it's gotten us there, but with that same type of testing, we just need to alter a little bit and utilize that more in looking at well health versus human health, not to get past the human health aspect. So the guidelines for the Canadian Drinking Water Quality are enforceable standards, and they're set through the Federal Provincial Committee as well as the advisory with Health Canada, and the regulations are broken up into 3 main categories. We've got our microbiological, our chemical and physical, and our radiological. Largely, you know, these are set as pretty good sense goals. I know at times, you know, even down south, we'd be grudging. Usually these are not just willy-nilly and dropped. You know, for example, the coliform rule, you know, came out of a defined need and fatalities that occurred. So it's developing, but understanding where that testing is more practical, that's really where we're at today. Just as kind of an overview on the primary guidelines there, I just pulled a few of them out. Arsenic, ethylene, ethylbenzene, and toluene. We've got our MAC level, which is our contamination goal there. Health considerations, it also gives you some potential insight. So if you're trying to investigate a contamination, it gives you some routes to check down. And then also there's some additional notes that I will say are much more beneficial in Canada than in the United States. These are real, what I would consider common sense on treatment guidelines, usually for larger wells and larger water systems, but pretty good direction and focus there. On the microbial side, these are pulled out and separated, and the chief one is the total coliform, and we're going to talk about that in the 3rd section on disinfection, but you know, largely it's an indicator of potential contamination, and from that, calling out fecal coliforms as a specific pathogenic type bacteria. We also look at enteric protozoa, Giardia and Cryptosporidium, and that's a good differentiation that we're not seeing in the United States. We look at all protozoa as being bad. There are a lot of problems there, but a lot of protozoas that are naturally occurring. So understanding they might be part of the recharge or just part of the soil microbiome is a very important consideration that I see here in Canada. Enteric viruses, and as an industry, we're still trying to understand that and the flow and activation of viruses in the subsurface. And then turbidity, again, as an indicator of problems. And total organic carbon is a good influence on that, but also if we've got a lot of root traces or biomass that are evacuated from the well system, that will trip our turbidity. So again, it's this balance, working within those. Don't use them as an endpoint, but use them as a guideline. And I'm going to talk about these in greater depth here, but if we're evaluating something like total dissolved solids or ORP or a manganese level or an iron level, it's the subtle changes over time that indicate a problem is occurring downhole. Maybe that's corrosion, maybe it's mineral scale buildup. On the biological side, tracking that population ahead of reaching a coliform is very important. And then we can schedule. We can schedule the equipment we need, the chemicals we need if they're necessary, and work with the client. Maybe it's a budget issue, coming up with the money, or maybe they need to find an alternate water source there. But it puts us in the driver's seat in addressing these problems. One of the big things in well health testing is how we sample. And I would always say this, and I say this anecdotally, jokingly, but it's very true, is if you've got a question, call the lab. I've got 5 people that work in our lab. They love to talk to people in the real world. Usually they've got the capabilities. Because of water quality guidelines, they always stay right within their lane there. But if you're trying to understand a problem, there might be a dilution or a secondary test that they can do, typically with very little additional cost because the preparation methods are all the same. That information can give you more insight into your problem. So please reach out to labs, discuss what you're seeing and what type of information you're needing. But with this, and where my talking will go the rest of this session there is we're going to look at just a few key parameters and how they impact well fouling. One of the issues here is if you've got a well that's throwing periodic problems, pull it offline overnight, 12 hours minimum, and collect a sample. Don't let it sit idle for over 24 hours, but collect that sample and you'll see what's really building up, what's concentrating, both chemically, biologically, and even mechanically. That first surge will bring up even sediment that's accumulated at the bottom. And then pump it a little while longer, start to flush out multiple well volumes, 3 to 4, and grab a second sample. And that comparison can really tell you a lot. This is the same well. From a water quality, the tap was flamed, it was pumped. This is good representation of what's coming into the aquifer. And it can tell us what to expect, but it doesn't really tell us the problems that the customer is seeing or that the filter is being impacted by. But turning it on, if it's sat idle overnight, completely discoloration, completely different biological and chemical parameters there. And that really told us what we needed to do as far as brushing, as far as how to chlorinate the well properly, and really put us in the driver's seat for decision making. So the information I'm going to present to you was over time period of 2020 to 2023. It's roughly 2,000 potable well pairs. So we had the static sample and then the active pumping sample. And again, we're looking at well health here. None of them were, hey, we're just sending in a sample for baseline analysis. So people were only coming to us with a problem. So this is and completely random as far as size, shape, completion method, materials used. These are the parameters we looked at. So total dissolved solids, alkalinity, hardness, manganese, iron, corrosion potential, total organic carbon, that was our water chemistry, iron bacteria, population census, and biodiversity was our biological side. So total dissolved solids, very easy parameter, can be run in the field. And it's a measure of the combined total of inorganic and organic materials in that water. Typically, the higher the TDS level, the higher visual turbidity is present. So this lightly kind of foggy type look there is indication that we're almost at the point of saturation with regards to a mineralized water. This isn't a pollutant, but it is a parameter that both in Health Canada and US EPA we evaluate for kind of general standards. Typically, we look at it at trying to be below 500 parts per million. Once we're above 500 parts per million, generally we see some taste impactions, greater potential for scale buildup. If it's even higher, upwards of 1,000, we can have some physical corrosion occurring. This is a good indication of a well that TDS had started to climb pretty significant over background levels, 30 to 40% greater, in fact. And in the downhole video here, this cloudy snowstorm is a whole mix of solids precipitating out of solution, some colloidal biomass. We even had some fine silts and clays that were infiltrating as the pump was operating into the borehole. Generally on TDS, we look at about 180 parts per million as our hard water limit. Below that, we consider it softer. Generally, it's more aggressive, but above 180, there's sufficient calcium, magnesium, and other dissolved constituents for scale to form. Average tap water across the continent, about 350. So this is by the time different water sources have been blended, they've been treated, they may have added additional coagulants for corrosion control, or in the States they add in fluoride. So generally it's heading out to distribution systems around 350 parts per million. Typical water quality treatment standard at 500. The freshwater limit, where we move into true brackish, highly congested waters, at 1,500. Kind of odd point of interest here, dogs, particularly water dogs like golden retrievers, Labrador retrievers, will turn their nose up at about 900. Cattle at about 1,100. Humans about 1,200, so who's smarter here?
Dog.
We get into salt, that real salty saline taste, at about 5,000. Now, I wanted to throw these in here too, and we'll talk about this a little bit more when we get into the cleaning aspect aside, but just mechanical cleaning of a fouled well. Running in with a brush or a swab, just working it up a little bit, you'll see that TDS, or conductivity, which is a function of TDS, spike upwards of 30,000 parts per million. And you can visually see that turbidity. But I call this out because if you're wanting to confirm, hey, we've fully flushed this well out, whether it's an existing well or even a new well, and you want to make sure you've developed it, look where your TDS or conductivity is. That'll give you a good indicator that you've flushed all that material out. Now, if we add in chemicals, whether it's simple disinfection or more involved like an acid treatment, and we're dissolving material or we're oxidizing material, breaking stuff down, we can easily go 100,000 parts per million or greater. And you'll see that in color. You typically will smell it too, but it's just that dissolved material and those introduced chemicals being flushed out of the well. So our average was 960 parts per million, fairly hard across those 2,000 sample sets. The highest we saw was in central Texas, where you've got a lot of karst topography, so you've got a lot of limestone that's dissolved naturally and carries that hardness into the wellbore. The lowest was in the Carolinas, and that's very soft water, very sodium-rich water. Also, kind of as a little side note, usually that water is fairly aggressive naturally, and so it's going to scavenge a lot of available iron and so forth, both from the aquifer as well as the well structure. Where we saw a change between the casing and the aquifer, average 24% fluctuation, so fairly considerable. Again, people typically reach out when the well's having problems, and when we're seeing that build up there, decline by 24%, that's suggesting to me that we've got a good chance for scale buildup occurring in those wells. High total dissolved solid and a water chemistry that favors scale. So when we've got a saturation indices or corrosion index that's in positive scale forming environment, 28% of the time. Alkalinity. Alkalinity is one of those parameters we forget about a lot. We run it in water quality because we need to identify it, but it plays into a lot of things. On the well design aspect, we use that alkalinity to figure out our stability index. How corrosive is that water chemistry? When we go to chlorinate a well, the alkalinity can provide buffering that limits the effectiveness of chlorine. Or if we're acidizing the well, if there's high alkalinity present, it can rapidly buffer and consume that acid, and so we end up needing more acid to digest the mineral scale. It primarily comes from carbonate and bicarbonate presence within the aquifer, although in some cases we have a little more negative aspect present. As I mentioned, we use this in a lot of parameters in well maintenance. Our highest occurrence was in the coastal influences in the Carolinas, 476 parts per million. And just to kind of give you a reference there, if you put in calcium or sodium hypochlorite into the well, at that level, it's not going to dissolve. It's going to stay that solid because there's just that much buffering capability. You typically need a lot more acid to clean a well in that area because the water is naturally neutralizing it. Our lowest was in central Georgia, near the kaolin mines. Again, that's where we saw the lower levels of total dissolved solids and some of our most aggressive water. On average, 124 parts per million. Once we get above 100 with total alkalinity, we can start to see its influences. If we get up to 200, it's doubled, 300 or got tripled, and then 400 quadrupled. So its impact is right in line with its scale there. As I mentioned, it hits both our materials investigation as well as our treatment. Oxides and hydroxides, really the most common scales we see in well systems. Predominantly iron oxide. Iron is abundant in the Earth's crust and our shallow subsurface, and a lot of our well structure is iron or iron-based. Even when it's alloys like stainless steel or HSLA, we still got a lot of iron present. So that is one of the reasons we see a lot of it built up in well systems. With shallow well systems, there's a lot of organically generated manganese, and then also in shallow wells, a lot of iron bacteria. So it kind of amplifies that buildup of iron and manganese scale. Generally, we need greater than a part per million iron. Manganese is at 1/10 of a part per million. So they're very similar elements. They behave very similar, especially in oxidative environments, but you need far less manganese to build up that scale. And manganese scale is a lot harder to break down and evacuate from the well. On the manganese side, highest we saw was 2.3 in Montana. The reason they call it the mineral state. On average, 0.51, so on average we were exceeding that 1/10 of a part per million by 5. Low wasn't uncommon to find 0. Generally there were other problems present. As I mentioned, the scale, 1/10 of a part per million. The water quality standard in Canada is 0.12, so right in line with that scale formation. Once you're starting to form scale, you're impeding your water quality. On the iron side, water quality standard is 0.3 parts per million, so we're going to catch it before it becomes a scale formation. In that 2,000 sample set, the average was 1.89, so that's your total dissolved and suspended. Our highest was again in Montana at 3.14. The resuspended iron test is a total iron test that also accounts for the biologically mobilized or entrained iron and manganese. Average was 7.54, highest was 205 in central Utah. And those are generally, we see those numbers spike in areas where we've got a lot of iron bacteria, a lot of rapid recharge of the aquifer, a lot of steel present. And we'll talk about this here in a few slides, but our iron bacteria rate of occurrence at this particular sample set was 46.4%. Generally in a given year, it ranges between 45 and 50%. So this is kind of right on par in the middle there. Water hardness, the mineral content of the water, it's a combined total of calcium and magnesium, typically expressed as calcium carbonate, so you're likely forming species there. Not a regulatory issue, but as you see in this piping section here, in a lot of the wells in hard water areas, it's a very common scale forming mechanism. And it's a mechanism that we typically have to incorporate a lot of mechanical energy and a lot of acid to break down and evacuate from the well. Water hardness differs across the continent. The white areas here are areas where we have generally soft water, below 50 parts per million. Then we go all the way to the dark areas are where we're above that 180 parts per million hard water limit. And you kind of look, it follows the Rockies right down to the Nemaha uplift and spreads out into the Texas area, but that's where you've got a lot of limestone, a lot of dolomite, so a lot of calcium and magnesium present. These pockets of white, like I said, the soft water areas, that's generally where you either have crystalline fractured rock aquifers or some basalt lava flows, generally softer water. That's typically, it's more aggressive, and generally a lot more iron and manganese issues in those areas where calcium and magnesium dominate where the dark blue areas are. With calcium, we need a neutral water chemistry, so 7 or higher on the pH scale. Alkalinity, 150 parts per million, so there's sufficient buffering capability. Hardness, it's got to be a hard water. Our LSI, our Langmuir Saturation Index, needs to be positive or saturated with respect to calcium, and then we need to have some calcium present. In this particular well here, where this column pipe came from, this is in a very geothermal active area. They've got all the attributes. Calcium is present. I think the base pH is 8.3, but the temperature is just below 100 degrees Fahrenheit. You practically see steam coming out of the well when it's pumping. And they're swapping these out roughly about every 2 years because the scale buildup is so significant. Average calcium was 183 parts per million, so on average we were dealing with hot water cases. Our highest was in central Utah, and you're probably starting to see a trend here that central Utah has a lot of problems with regards to wells. 1,700 parts per million. I mean, you turn on the faucet and it's chunky, kind of like the sea salt grater. Lowest was in Georgia, again that area with the lower pH, very low TDS levels, more aggressive type of water quality. Change in the casing in an aquifer of 10% or more, 31% of the time. And that was just, we're seeing a saturated environment develop, favoring calcium scale. Where we exceeded that 120 parts per million that we need for scale, occurred 63% of the time. Talked about it in a few slides, the Langmuir saturation indices. It's a logarithmic calculation that tells us the potential of either corrosion or scale formation downhole. It was originally developed in the boiler industry in the 30s. There have been a couple revisions to it over the years. The Reisner Stability Index, the Corius Index, the Larson-Skold Index, but the Langmuir is really kind of the grandfather of them all. Tends to be, pretty spot on in giving us guidelines. We use a lot of standard water quality parameters: pH, total alkalinity, total dissolved solids, calcium content. And what it gives us is it gives us a number between -7 and +7. The negative values are more aggressive, more prone to corrosion, especially of more reactive materials like low carbon steel or galvanized steel that's got a nick in it, or poorly coated steels. The positive is more scale forming, it's a more saturated environment, so when we've got the positive number on a new well, we know that we're going to be rehabilitating that well periodically, and we're going to be using acid, so we try and factor that in. When we've got a negative side, we're going to look at less reactive materials, maybe a PVC stainless steel hybrid, or PVC top to bottom, or stainless steel top to bottom, depending on the customer's needs. Lowest was in East Texas at -4.39. They put in real thick wall steel because they just assume they're going to be losing it. And so conversely, they're doing a lot of iron removal from those wells. Highest was 1.67 in Southern California. Typically warmer water, highly mineralized down in that area, a lot of buffering potential with alkalinity, knocking on the door of around 300 in that area. Our average across the United States is -0.36. So on average, more aggressive, and I'm honestly saying more aggressive than we designed for. Anyone happen to read about the Flint debacle that occurred in 2016? So brief, what happened in Flint, Michigan is they changed the water source. Now, surface water on both water sources, but the new water source was more aggressive. No one thought to look at the water chemistry. They just made sure they could treat it, but they didn't look how aggressive that water was. And switching to a more aggressive water, then they had a lot of failure points and old connections, moved a lot of lead that was in the system still, and so a lot of contamination from that event. Well, after that, the USGS, which is charged with monitoring groundwater quality in the United States, they went through their records, and they maintain water level measuring wells, active wells on national parks and federal properties, and then they also maintain the private well owner network, which is purely volunteer. So not a complete data set, but really the first time anyone looked at water quality across the United States from a corrosion standpoint. And they just evaluated the LSI, that calculation I just showed you. And what they found was that corrosion was in 50% or greater of the wells. And this kind of explained to me why we see so much iron in our well systems. But I can tell you that a lot of our wells were not designed with that. And so we've got longevity issues. And that's one thing, an argument I'll make throughout the day here is our customers are demanding more. whether it's the cost of materials, the cost of labor, the cost of proving the water right, whatever it happens to be, is wells are more expensive than ever before. Maintaining them is more expensive than ever before. And so we're being asked to design wells with longer longevity, more operational life. And so keeping this in mind, running some of those additional parameters can help us in material selection, and then also kind of give us some guidelines for that owner moving forward of what they need to expect. Total organic carbon, it does have influence on the microbial community. Generally, it's an indicator of stimulant. So the more dissolved organics that are present in the water, more likely you are to see bacterial activity and bacterial growth. It is one of the standards on the water quality standards for Canada under microbial testing. So we do have some goals there. We don't use it as an end-all, but we use it as an indicator of potential problems coming down the pike. When it's above 1 part per million, then we start to have some concerns depending on the population. The average we saw was 2.66. So again, these are fouled wells. Organics are starting to build up or concentrate in the well. A lot of biological issues, so that checks out. The highest we saw was in the coastal influence areas of North Carolina. That water, as you would expect with a TOC of 19, it looks like sweet tea. And so I'm not really sure if they can tell the difference sometimes with their drinking habits, but just aesthetically wise, not a very good quality water. Lowest, a lot of places we had a 0, and we still have biological issues, but we tried to track it and monitor it. Generally, we find higher readings in alluvial aquifers, and this is because you typically see rapid recharge from a surface water body, whether it's a gaining or losing stream, or coastal area, or a lake area. A lot more organic influence there. Generally lower in the aquifer samples, because the concentrating occurs when the well is idle and offline. Bacteria-wise, some of the ones we look at, because they're common problems that we see in wells, are slime formers, our iron and manganese oxidizers, anaerobic growth, and specific within the anaerobic community are sulfate reducers, and then coliforms and pathogens from a direct aspect of human health. The 5 most common species that we identified: Gallonella, that's an iron bacteria; Pseudomonas and Bacillus, some of the most prolific slime-forming bacteria on the planet; Acidovorax, a soil microbe; and Acinetobacter, another soil bacteria, so common in the recharge environments. Iron bacteria, these are bacteria that derive their energy from iron. They secrete a little bit of acid right in to digest the metal and then consume that iron. And if you pull that organism away, you'll find a very small pit. If that organism is allowed to continue to munch on that iron, that pit will grow, as will the bacteria itself and the bacteria's waste stream, which is a little washed out, but it's this chain of sausages, and it's an iron oxyhydroxide. It's a very sticky, slimy form of iron. It will come out bright red. As it dies off, it starts to go to a reddish brown and then to brown. I've seen these as long as 3 foot or just close to 1 meter in length in a very heavily infested well system. They are the most active agent of microbial influence corrosion. And it's not just that pit that they form, because even stainless steel, which has a lot of passivation, a lot of protection against corrosive environments, it is broken down. And so you'll see the point of attack with that pit, but the acid attack will depassivate an area around that pit. And so that steel is that much more vulnerable moving forward. Low carbon steel, HSLA, and stainless steel alloys, all vulnerable to that. There are some tests. The BART, Biological Activity Reaction Test, will confirm the presence or absence and general growth range of iron bacteria. The best way we have found is confirming it under the microscope and getting an assessment of what type of growth has occurred. So is it pretty pronounced like this, or are we just in the early stages? Between 2020 and 2023, our occurrence rate was 46%, so fairly significant. Iron bacteria, 75% of those that we identified were Gallonella. And the Gallonella, there's a lot of bad press. A lot of people think, well, the contractor introduced it into my well. The fact is, it's a soil bacteria, it's common in rapid recharge areas, it's going to be natural to that aquifer. And what we've done in drilling that well, we've added in a little bit of heat with the drill bit, we've added in oxygen. We've mixed up a bunch of water chemistries, and in some cases we put steel in there. So we've created a perfect environment for the iron bacteria to awaken and then start to consume. So it's naturally occurring, it's not introduced, it's just a point that we've created that perfect environment for them to propagate. Sulfate reducing bacteria, this is an anaerobic growth, so it's a bacteria that lives in a low oxygen or oxygen depleted area. So if we've got a sand trap or a blank space at the bottom of the well system, or if we've got a real tight formation and we've maximized our screen, but we're only getting maybe 3-5% flow out of the bottom area, we'll see it down there. If we've got an area of poor development where we're not getting flow, we'll see our anaerobes start to prosper. And what this particular bacteria does is it reduces sulfates or sulfites to sulfides. And in doing so, it releases hydrogen sulfide gas. In a local sense, in the water column, it can drop the pH up as much as 1.5 from normal. So it can turn a neutral water into a corrosive water pretty quick. Generally what we detect, and more so before COVID, because a human nose could pick up 1/10 of a part per billion of hydrogen sulfide before then, we'll catch the odor as that gas moves up the column. Especially if the well's been idle, you turn it on, you get a rotten egg odor right away and it starts to dissipate. That's a solid indicator that you've got SRBs downhole. The occurrence rate was only 12.6%. Some areas that's been higher, other years it's been lower, but not an uncommon issue, but not the most common. More often than not, there'll be a wisp of it. And it tells us, hey, we've got fouling occurring. It hasn't maybe graduated to SRB levels yet, but it's already developing. Coliform bacteria, and we're going to get into these in the last session of the day a little bit more, but it is the industry standard in Canada and the United States for water quality. It's a very easy test, it's a very cheap, very efficient test. It can pick up 1 in 4 billion. And so it's very adept at identifying coliforms. There are bacteria that can trip it. If you've got a very heavy load of bacteria in general, that can throw off the test. There are some slime formers like Aeromonas that can trip the test. So if you've got a coliform bacteria, ask, is it a fecal coliform? And if you can, get a count to identify what the true problem is. But we use it as an indicator. More often than not, when we are finding coliforms in a well, the well has either been out of service for a couple of years, or it's just heavily fouled and we've reached that point of evolution, if I may. This is coliform occurrence versus anaerobic growth. And anaerobic growth is reported in percentage of the total population. So 10%, 15%, we generally don't get too concerned, but when we start to see greater than 20% in a well, we know we've got a pretty advanced level of fouling, or we've got a dead zone in that well where flow's not going through. Well, at 10% or less, our coliform occurrence was pretty low, less than 2%. As we climbed 15%, our occurrence was at 25%, and we got to 30% or greater at almost 50% of the time. So generally when we're at 40, not only do we have coliforms, more than likely we're going to have sulfate reducers and a lot of other issues, generally some mechanical fouling downhole as well. Coliform occurrence versus others. So in that 2,000 sample set, coliforms occurred 6% of the time. E. coli occurred 1/100%, so very rare occurrence there. But the occurrence of either iron bacteria, sulfate reducing bacteria, or a very high population load, 60% of the time. And this is a good indicator. I'll have clients, wells of all shapes and sizes and well fields that are similar. Well, I've been testing and I don't have any bacteria. Well, you've just been testing for coliform, and you're lucky. You don't have any of those indicators. But you could be having iron bacteria, you could be having SRBs, you could be having an excessive level of bacterial growth. An ATP of 5,000 is about 5 times the fouling threshold. Excuse me, an ATP of 500,000. So with testing, this change, it's a mindset change. It's explaining to our customers, it's explaining to our coworkers and within the industry, hey, our health standards are great, but we can't use those because that's an endpoint for our well systems. We can use a lot of the same test methods, Maybe look at them a little more frequently, start to compile the data, look at the differences, not just crossing a threshold level, but see how it's building up. Or if it's not, that's okay too. Regular testing, and so people will ask, well, do I need to test every month? You need to tell me, what role does that one well play to you? Is it part of 10 and you can pivot to use another water source? If that's the case, maybe you test every 2 years. If that's your only well system, you want to test more frequent. And if it's prone to problems, and those problems are expensive, test even more frequently. The host of issues here that I've looked at and the parameters, we're talking at less than $100 testing. So it's not a very expensive deal, and it catches you ahead of time. So then you can schedule your maintenance efforts or the materials that you'll need. Look at how we're collecting the samples. Again, if you're really trying to investigate, I advocate looking at a static sample and an active pumping sample and comparing those results. If you get to the point where you're starting to do that and you want some insight, feel free to reach out to me. I've written a few articles on this. I'm more than happy to share information and guidance on what to look for and how frequently, depending on the well system. Document everything. Even if we had a failure in cleaning or the disinfection didn't go well, let's document it. Let's learn from it. Let's understand why that didn't work, so the next time we go out or the next well, we're responding more effectively. And then review the data. I've got a lot of medium-sized municipal water plants, and the water operator typically wears a variety of different hats. They're on volunteer fire department, they're also the dog catcher and the deputy sheriff. And they get the data, it comes in, oh, we didn't exceed water quality goals, we're good. Well, that just goes into a folder that's covered with dust. Let's break that out. Maybe it's just once a year, but let's look at those changes that occur. And again, catch them early, we can react a lot more effectively. It's going to move the lifespan of the well a lot better when we're not just running to failure on a cycle. The same with the pump systems. So this is our first break that I've got scheduled. Going to leave some time here for questions with regards to testing. The next session gets into chemicals and well maintenance, and then the following one after that is disinfection and the coliform test, and a little further in depth on biological testing. Questions today? I'm open for that, but also this is my email address and my office number. As I mentioned, feel free to reach out. More than happy to give you some guidance. I've written a number of articles for Water Well Journal and for a lot of the state associations on the phenomena that we will talk about today, so I'm more than happy to share that information with you. So, questions? Okay.
It's a little bit, I think it's a little bit over most of our heads. That's my own.
No, fair.
It is.
There's the lab people, myself included, don't always get to share this information. So it's a lot more than we as an industry look for. But I think, we're getting to that point where people are asking more of us, and at least in Kansas and in my backyard, there's fewer of us doing it. And so, the joke that a couple of us have is the easy water's gone. The easy projects are gone. And so we're getting more challenges, and we're having to look a lot deeper, no pun intended there, trying to understand why these failures are occurring. And I've seen in some cases where, especially larger municipal systems in the West, they want a guarantee of a 100-year well. How do you work with that? We all have customers that are using wells long past their lifetime, so we try and learn from that. One of the big things is corrosion, and then how are we operating it? So I always heard this comment, and I didn't understand it until I had a teenager myself. An idle well is like a teenager; no good can come of it. So that's one of the first things is when people have a problem, like, well, how are you using this well? Are you pumping it to its maximum and increasing drawdown and mobilizing sediments and forcing problems? Or are you using it hardly at all, and then the reverse is occurring?
So it's like everything else, nothing general is going to work.
Exactly. And no silver bullet. And that's, the more information we can get out, and we as an industry can have, or at least have within our network, the more of these problems that we'll be less surprised over, or there's someone we can reach out to get some more insight. Was there a question in the back?
Well, you kind of answered it. I was gonna say, can a lot of these problems will cause from over pumping the well? But not mentioning that.
They can, you know, and the easy one is if you expose screen. You get a lot of aeration and oxidation. But on the other side, even when you're not exposing the screen, you know, there is a pressure differential that will force things out of solution and you'll force scale development. Also, especially in alluvial aquifers, that overpumping mobilizes sediment at a faster rate, which then leads to mechanical fouling, and then that also opens the door for anaerobic growth. Okay, it's 1:53. How about we meet back here at 2:05? Sounds good?
Yep.
Thank you, everyone.